Well, one of the great mysteries in modern astrophysics, as indicated by the recent Astrophysics Decadal Survey, is the formation of the first stars and galaxies in the very early universe. We proposed a mission called DARE, the Dark Ages Radial Explorer, which for the first time will investigate this unobserved very early epoch in the universe at redshifts between 11 and 35. This corresponds to time scales of about 80 to 400 million years after the Big Bang. We're going to do this by using the hyperfine transition of 21 centimeters from neutral hydrogen. And because we're using that line, it's redshifted to very low frequencies. DARE will operate between 40 and 120 megahertz, so very low radio frequencies. Because of that, we're really driven to the moon, because the moon is the one place in the inner solar system, at least the far side, where it's been proven to be radio quiet at these low radio frequencies. We have proposed this mission now to NASA as part of the Explorer program, and it's currently under review. We have an extraordinary team of co-investigators that you see listed here. The project management is being done right here at NASA Ames, and you'll recognize many of you Dan Andrews, who's our project manager. The spacecraft will be managed out of Ball Aerospace in Boulder, and the instrument, namely the radiometer, at JPL. Well, here in a nutshell is the science that we're going after. We want to understand the first billion years of the universe, which is, as I said, largely unexplored. What you're looking at here is a cartoon picture of the history of the universe, beginning with the Big Bang up over here, and then down below is about 14 billion years later, today's universe. It's a logarithmic timetable that you're looking at, and a few redshifts are also indicated on the right-hand side. Up here, the CMB, that's the cosmic microwave background. That's the first observational signpost in the early universe. This is a so-called epoch of recombination, when the first atoms come together, electrons and protons, forming neutral hydrogen. The universe becomes transparent for the first time, and we get a picture that we probe with satellites like COBE and today with Planck. After that time, the universe really goes dark. The reason is that the traditional sources of radiation, namely stars and galaxies, haven't formed yet. So there's nothing there to illuminate the universe. And so astronomers have dubbed this the Dark Ages. Okay? And a little bit later, though, as things progress on, there's a lot of activity that's actually happening. You have collapsing cold clouds of neutral hydrogen coming together to form the first stars. And several hundred million years after the Big Bang, according to models, those first stars, which will be very large, probably 100 times the mass of the sun, or even a little larger, will be formed. They'll go through their lifetime very quickly, explode as supernovae, and produce hot bubbles of ionized gas around them. That's these little fuzzy, sort of greenish blobs that you see there. As time progresses, more of these overdensities will collapse, form stars, and you'll begin illuminating some fraction of the universe and forming the so-called cosmic dawn. This progresses until these hot bubbles actually begin to overlap, and so that by the time you're about 1 billion years after the Big Bang, redshifts roughly 6, this will be the last phase transition in the early universe, going from an all-neutral intergalactic medium to an all-ionized intergalactic medium that we observe today. Now, as I said, this is all theory. Makes sense. But it is literally unobserved to the present time, and that's the purpose of DARE, is to go in and explore this for the first time. Now, as I said, we don't have the traditional sources of illumination during the Dark Ages and cosmic dawn, but we do have a lot of neutral hydrogen. And fortunately, nature has provided a signal at 21 centimeters from the hyperfine line of neutral hydrogen. This is at a frequency at rest of 1420 megahertz. How does this work? Well, if you look at the ground state of neutral hydrogen, it actually has 2 hyperfine levels depending upon the spin states of the electrons and the protons. When those are aligned, that's the upper state. When they're anti-parallel to each other, that's the lower state. And a transition from the one to the other produces one of these 21 centimeter wavelength photons. Now, what's interesting is because we're looking at the very early universe, these wavelengths are redshifted, the frequencies are reduced, so that at a redshift of 6, for example, that corresponds to 200 megahertz. At a redshift of 35, which is well within the dark ages, you're down to a frequency of only 40 megahertz. So once again, this drives our experiment to the low frequency regime. Here's a cartoon picture of the radiation transfer of a process that goes on. Here's our spacecraft in orbit of the moon. Here is a cold collapsing cloud of neutral hydrogen, and that cold cloud is bathed with a backlight from the cosmic microwave background, such that when radiation passes through the initially cold cloud, at early times at least, you will get an absorption signal, an absorption line that will be observed by the spacecraft. When you work through the equation of radiative transfer in more detail, the power that will be perceived by the receiver, or the brightness temperature, as radio astronomers like to describe it, will be proportional to the neutral hydrogen fraction, the baryon density, and the difference in the characteristic temperature of this cloud, called the spin temperature, and the CMB temperature. Now, going in more detail, two of our collaborators on this project, Pritchard and Loeb at CFA Harvard, published a paper at the end of this last year that looked at a model for what we'd expect to see from an all-sky signal. That is, from looking at a large region of the sky, what the sky average signal would look like. And what you're seeing here is power or brightness temperature versus frequency. And because we're dealing with the 21 centimeter line, each one of these frequencies maps directly into a redshift and to tell us about events in the early universe. And as you can see, this spectrum, particularly in the DARE window in here, which is in orange, is filled with some very interesting features. B, our turning point here, is when stellar ignition occurs. That's when the first stars turn on. Those first stars emit ultraviolet light. As it turns out, that ultraviolet light interacts with the hyperfine states of neutral hydrogen and drives an absorption trough. So this turning point tells us uniquely when the first stars turn on in the universe, something that we don't have a measure of today. A little bit later on, the first black holes, according to models, also form. They may be the remnants of those large first stars. Those black holes turn out to be very important because surrounding the black holes will be accretion disks which heat up and emit X-rays. According to models, the X-rays are key to making the transition from a neutral to an ionized universe. So those X-rays begin heating and ionizing the intergalactic medium. That drives a signal from absorption into emission. We have another turning point here which we can measure. That's the turn on of the first black holes. Up over here from D to E, at this point now, we're beginning to see a significant fraction of the universe becoming ionized, and that signal is driven by the fraction of neutral hydrogen left. So the turning point D here is an indication of the beginning of the end of the epoch of reionization. So what we're going to do with DARE is to produce the observational counterpart of this theoretical diagram. The science in a nutshell, which was featured in the Decadal as one of 3 science priorities for this next decade, are best framed in questions: when did the first stars form? When did the first accreting black holes form? When did the epoch of reionization begin? Those are our key points. We're going to do this experiment at the moon. The reason is we need to get away from the RFI on the Earth. It's a major foreground on the Earth. We're going to take a slow ride to the moon, very similar to what Grail is doing around one of the Lagrange points, and then into a circular 200-kilometer orbit, not because that is the most efficient, but simply because it is the most cost-effective. It's a low delta V orbit, low on fuel, and we'll take data only above the far side, which is the radio quiet zone. We're not out of the woods. There are significant foregrounds, also cosmic foregrounds, that we have to look through. Our galaxy in particular is a strong source of what's called synchrotron radiation. Here's a map of our galaxy at 70 megahertz. These relativistic electrons, which are in the interstellar medium, they radiate via magnetic fields, and the emission is quite strong. In addition, we also have foregrounds coming from our sun and also from the moon, including reflections of the galaxy off the moon. The nice thing is when you look at the spectrum from the inner mind to the outer limits, so you get the spectrums you're looking at here. Our 21 centimeter spectrum that we are looking at is full of features, whereas the foregrounds, the galaxy and the moon, are all spectrally smooth. That's very important because we're going to use that to contrast one from the other and be able to pull out this very weak signal, which is 4 to 6 orders of magnitude smaller than the foregrounds. So to do that, we need also an instrument with a very smooth response function, and this is what we have come up with over here for an instrument that is a biconical tapered dipole antenna that you're seeing up from above here. It's located on the spacecraft here, supported by the frame, and just below it are these radials that serve as a ground plane that help reduce the back lobe, which will be emission coming off of the moon. As I said, it produces a very nice spectral response function that we see here. Ricky, okay. There should be a movie here. I don't know if you can try to activate that. That shows the spacecraft going around here. One final point, which is very important, that is the spacecraft itself obviously must be very radio quiet. And fortunately, our collaborator, Ball Aerospace, has built a similar satellite about 10 years ago called DARPASat, similar at least in the sense of being radio quiet. But Greg, if you ask me anything more about that, I'll have to shoot you. So I just can't tell you anything more about that. But finally, the calibration technique is very important, the differential spectral calibration, which I will refer you, rather than go through the details of this, which are somewhat technical, to Geraint Harker's poster, which is up now. We use something called a Markov chain Monte Carlo code, which is similar to what the cosmic microwave background folks. The secret here is to really compare the 21 centimeter signal full of features characterized by these turning points against the spectrally smooth foregrounds. When we compare the signal that we put into the extracted, we do very well. This table has details on that, which I won't bore you with, other than to say that we can measure the frequencies of the turning points at the 90% confidence level to better than 10% for the lowest frequency and better than 1% for the 2 highest frequency turning points. So to end, we have Natalie Portman here from her advertisement of a movie from a few months ago, really pointed the way for us right here. Dare to be bold. We're going to measure when the first star is ignited, when the first black holes turned on, when reionization began, and we're going to do that by constructing the first sky average spectrum of the redshifted 21 centimeter signal. And finally, just want to acknowledge that there will be further presentations on this from my collaborators Lazio and Furlanetto on Thursday, and 2 poster presentations that are up now. Thank you.
Thank you for an amazing example of science from the moon. Do we have any questions?
I'm going to have to shoot you. I'm going to have to shoot you.
Thank you. Greg Schmidt, NASA Lunar Science Institute. I wanted to ask if you could comment on some of the exotic physics that DARE might be able to observe at some of the higher Z numbers.
Yeah, thanks, Greg, for that question, because one of the things that is interesting, I didn't have the chance to talk about, is that if, for example, there is dark matter decay, which many models do predict, at this very early epoch in the universe when things are particularly simple, that's going to be a source of heating on the intergalactic medium, and that will make an imprint. We have worked with some of the models to show what the influence would be, for example, on the spectrum, and it does produce some characteristic signatures that we would certainly keep an eye out, because this would potentially be the first detection of dark matter.
Yeah, Jack, assume for the moment we didn't have a moon. Without the
presence of the moon there that you take advantage of, how could you make these measurements? And if you could, what would the circumstances be, and how would it change the projected cost and complexity of the mission?
If we didn't have a moon, we'd have to make it, and because we need a big shield if we're going to do this in the near the Earth. Otherwise, what we would do is go pretty far out into the solar system, so the 1/r² effect of the radio frequency interference would diminish.
Did you happen to assess how far you'd have to go?
Yeah, we looked at this. I think, Joe, do you remember? Yeah.
Different mission.
It is.
One question over here.
Rafael Garcia from France. Why not landing on the far side?
The only reason we're not doing this with a landed mission is cost. An orbital mission is much cheaper, but you're absolutely right. We could do this and do it even better. In fact, what we would hope is that the next generation will actually then, as I'll talk about on Thursday, will be an array on the lunar far side that will not only allow us to detect this signal, but actually resolve the structure that's expected in the 21 centimeter signal that is going to tell us a lot more about cosmology.